Imagine a world where AI doesn't just predict the next word, but understands the structure of reality itself. Not through brute force training, but by learning the fundamental rules that govern how things change, interact, and evolve over time. This isn't science fiction. It's the emerging frontier of physics-informed AI, where neural networks are no longer just pattern-matching machines, but intelligent simulators of physical laws. At the heart of this revolution is a new class of models, differentiable physics engines. These aren't just AI systems that learn from data. They're systems that encode the laws of physics directly into their architecture. Think of them as neural networks that don't just memorize how a pendulum swings, but actually understand the differential equations that govern its motion. Let's dive into how this works. Traditional deep learning models like transformers or CNNs are powerful pattern recognizers. But they're blind to causality. They see that when a ball is dropped, it falls, and they learn the statistical correlation. But they don't know why. They don't understand gravity. They don't model inertia, acceleration, or energy conservation. And that's a problem when you want to simulate complex real-world dynamics, especially in domains like robotics, climate modeling, or drug discovery, where physical fidelity is non-negotiable. Enter physics-informed neural networks, or PINNs. Developed in the early 2020s by researchers like Navier-Stokes and George Karniadakis, PINNs embed the governing equations of physics, like Navier-Stokes for fluid dynamics, or Maxwell's equations for electromagnetism, directly into the loss function of a neural network. Here's how it works. Instead of just minimizing prediction error on observed data, the model also minimizes the residual of the PDE, its deviation from satisfying the physical laws at every point in space and time. For example, suppose you're trying to model airflow over an airplane wing. You have sparse sensor data, maybe just a few pressure readings. A standard neural network might interpolate between them, but it could produce a solution that violates conservation of mass or momentum. A PINN, however, is forced to satisfy the Navier-Stokes equations everywhere, even where data is missing. The network learns both the solution and the underlying physics simultaneously. But here's the real breakthrough: differentiability. Modern deep learning frameworks like PyTorch and JAX allow us to compute gradients through these complex physical simulations with perfect precision. That means we can train neural networks not just to approximate solutions, but to learn the parameters of the physical system itself. This is where physics-informed learning becomes truly powerful. Imagine you're studying a complex chemical reaction, but you don't know the exact reaction rates. A PINN can be trained on sparse experimental data, while being constrained by the reaction-diffusion equations. The network doesn't just predict concentrations. It inverts the physics to estimate unknown parameters like diffusion coefficients or activation energies, all while ensuring the solution remains physically valid. And it's not just about solving equations. We're now seeing models that learn entire dynamical systems from scratch. Consider the concept of neural ODEs, continuous time models where the hidden state evolves according to a learned differential equation. Instead of discrete layers, you have a continuous flow governed by a neural network that defines the derivative of the state at any point in time. This is transformative. Neural ODEs can model systems with irregular time steps, handle missing data gracefully, and even extrapolate beyond the training period, something traditional recurrent networks struggle with due to vanishing gradients and fixed-time discretization. But the most exciting developments come when we combine multiple physical principles. Researchers at MIT and Stanford have developed models that integrate mechanics, thermodynamics, and even quantum behavior into a single neural framework. These are not just AI assistants. They're digital twins of physical systems, capable of simulating complex phenomena from galaxy formation to protein folding with unprecedented accuracy. And the implications? Massive. In materials science, we can now simulate how a new alloy behaves under stress without running thousands of physical experiments. In climate modeling, we can run high-resolution simulations of atmospheric dynamics with far fewer computational resources. In medicine, we're using these models to simulate blood flow in patient-specific arteries, enabling personalized treatment plans before a single procedure. But there are challenges. Physics-informed models aren't magic. They require accurate physical laws to begin with. If the governing equations are wrong or incomplete, the model will learn the wrong physics. They're also sensitive to noise in data and can struggle with chaotic systems where small perturbations lead to large divergence. And training them is computationally intensive, especially when solving high-dimensional PDEs in 3D space over time. Yet despite these hurdles, the trajectory is clear. We're moving from AI that learns from data to AI that learns from principles. This shift is not just incremental, it's paradigmatic. We're no longer just teaching machines to imitate the world. We're teaching them to understand it. The future of AI isn't just smarter algorithms. It's smarter physics. And in that convergence, we may finally unlock the next great leap in scientific discovery, where artificial intelligence doesn't just predict the future, but helps us design it. Because when machines learn the laws of nature, we don't just build better models. We build better understanding. And that changes everything.